So today we start Unit 7, which is on energy. Now most of you guys have learned about energy, previous classes, which is good. None of that stuff is wrong. So if you remember that, you're ahead of the game. If not, this isn't too bad. So here, it gives us the definition of work. Now, this seems like a very, oh, why does science got to be different than everything else? It's because we're trying to be very specific. And so for a lot of things, you guys should have noticed this, bless you, that in your labs, you'll notice that we always start off with questions of like, what is the system? What is the environment? Does the environment affect the system? Stuff like that. The reason why we do that is because a lot of things when it comes to energy is talking about work. And the definition of work is it's the transfer of energy, okay? So if you know what your system is, then we can say work done on the system means energy was given to the system somehow. Work done by the system means the system got rid of energy, like it did work on something else. And so work is simply the transfer of energy. So in order to have work, energy has to move from one place to another. And so that's the definition of work, the transfer of energy. If no energy is being transferred, no work can be done. So the definition is the transfer of energy, and we can see here how it's calculated. Work, the symbol is W, is equal to force times the distance over which that force is applied. Okay? So if you push, let's say, a lawnmower, okay? You apply force, the lawnmower moves 3 feet. You did work, okay? You apply force over a certain distance. Now, the work has a unit which we haven't seen before called joules. So unit for force is newtons, unit for distance is meters. And it turns out when you multiply newtons times meters, you get the definition of a new unit called joules. Joules is the unit for energy in the metric system. So anytime you see joules, you know, okay, I'm talking about energy. So we're going to see it here for work. But as we talk about different types of energy, you'll keep seeing that word joules again and again, because it's just any energy is joules. And I've got good news for you. Work is not a vector. Okay? It doesn't have a direction. It just has a sign. Right? However, force and displacement most definitely are vectors. And so it turns out what we're doing here is we're taking two vectors and we're making a scalar, so it doesn't have a direction, which is nice for you guys. But you got to be a little careful when it comes to calculating it, because it says right here, the objects must move in the same direction as the force applied. Which makes sense. If you're pushing a lawnmower and the lawnmower is going forward, well, you're applying force and it's going in the direction you're pushing, right? The reason why we have to make sure they're going in the same direction is because you're transferring energy to the lawnmower, right? You're pushing the lawnmower and now it's moving. It has energy because it's moving. Where do you get your energy from? I guess eventually, yes. I was talking about a little bit more closer to home. Food, right? You eat food, you get energy. Make sense? Technically, yes, it all comes from the sun. But more specifically, you eat food to get energy, right? When you eat food, what is your food energy measured in this country? Calories. Y'all are familiar with calories? Now, turns out, because the English system of measure is so fun, there's actually two different sizes of calories. There's like the little calories and big calories. And little calories are actually the same thing that we use for joules here. Let me get my tools up. This one. Not like we're doing that, is it? Whatever. Okay. So So if joules and calories are essentially both measurements of energy, you should be able to convert from one to the other. Now, we're not going to spend too much time doing that, but I want you guys to realize there is a conversion. So 1 joule is equal to 4.1, that's right, 1 calorie, little calorie, is equal to 4.186 joules. So a joule is a bit smaller than a calorie. You need about 4 of them to make 1 calorie. Does that make sense? So that's a little calorie. That's not the calories that are used to measure your food. The food calories are actually what we call kilocalories, and they're represented by a big C. So 1 big C would equal 1,000 little calories, which equals 4,186 joules. Does that make sense? So I want to kind of express this to you because when we're talking about energy, it's all energy. Energy is energy, and you can change it from one form to another. Now, you're not going to be able to use any form of energy, for food, but they're all different forms of energy, and we can use them to do work. We can use them to apply force over a distance, and we're going to talk about that in the upcoming days. So it's important to know that, like, when we do the horsepower law, you guys are going to do work, and you're going to calculate how much energy you use. And it's going to be, probably a couple hundred, if not a couple thousand joules of work. And you're like, man, I did a lot of work. And then you can think about, like, okay, well, to live every day, you have to burn calories, right? That's the energy you make. So you eat food, you burn food. That's how life works. And so people will see this and be like, oh, gosh, maybe you did, 4,000 joules of work going up the stairs. How many calories did you burn? 1. Fun fact, you might ask yourself, well, how many calories are in, say, like a pound of fat? Well, 1 pound of fat, in American systems, is about 3,500 of the big calories. So simply going up the stairs might burn 1 calorie, but if you're trying to get rid of a pound of fat, you would have to go up the stairs over 3,000 times to burn 1 pound of fat. When you start to look at that, you start to realize, like, it's actually kind of difficult to burn fat. There's actually a lot of energy in it, okay? I say this not to discourage you, but I want you guys to realize the reality of the situation. So what is energy then? Because work is the transfer of energy. Well, what the heck is energy? Well, energy is the ability to do work. That's a very circular definition. I like to say energy is the ability to produce a change. Right? And so there's many types. There's a list up here. That's not a complete list. I'm not going to sit here and list out all the different types of energy. And, a lot of times you hear about this, like in the news, they talk about different types of energy, talk about, kinetic, not kinetic, but like solar energy, chemical energy, like gravitational potential energy. What I think is interesting is, like it doesn't, obviously there's stuff on here like hydroelectric and stuff that's not on there, but these are all different forms of energy. Your food essentially falls under which category? Food, where do you think falls here? Chemical. Does that make sense? Now technically gasoline energy would also be a chemical. However, I don't recommend drinking gasoline. Where are you?
Oh, it's easy.
See it. All right. I have you sitting there. Not here, but there. Okay. So, yeah, there's many different types of energy. And, kinetic energy is like the energy of motion. I think most of the rest of these are pretty self-explanatory. One of the interesting things I find is gravitational energy. Gravitational is just like the energy because of something located in a gravitational field. We like to call gravitational usually gravitational potential energy. And so potential can be slapped on top of a lot of these labels. Like you can have potential chemical energy, chemical potential energy. Or elastic potential energy. It's just any energy that is stored. Like that is what the word potential means. Growing up, my mom used to say my brother had a lot of potential. If he would only get off the couch. My brother actually had a competition to see how lazy he was. Turns out he won. Because of him, I found out that the Disney Channel apparently plays the same thing every 12 hours. He knows because he sat there for it. So potential means stored energy. It doesn't mean that you're using it right now, but you might use it in the future. And so a good example of gravitational potential energy is actually water. Like the water that comes out of your faucets or the water that we use for our toilets. That's actually stored in the water towers. Like up. How many of y'all have noticed that even when your power goes off, the water still works? Because your water is powered by gravity. So even if all the power goes off, as long as the pipes aren't busted, you still have water. And you'll have water basically until that power runs out. So that's just an example of gravitational potential energy. So work, again, is force times the distance. And so whenever you go to calculate work, the first thing you have to ask is work actually happening? Because I gave the example of pushing a lawnmower. You apply force, it goes this distance. However, you pushing the lawnmower, that's not the only force acting on the lawnmower. For example, if you're pushing it in grass, well, you're going to have a lot of friction pushing back against the lawnmower. And that friction, is that going in the same direction as the lawnmower? No, it's going in the opposite direction. So in that case, if I apply the force that the grass is applied to the lawnmower times the distance over which it's applied, I actually get a negative work. And in this case, the negative work isn't a vector, but it's just like it's taking the energy away from the system. Which makes sense, because if you push a lawnmower and then just like shove it, like out in front of you, does it just roll forever? No, you get that friction that will take the work away, take that energy out of the system. So, it says if you push a broken car with 1,000 newtons of force, but it doesn't move, how much work did you do? Well, what's the force? 1,000 newtons. What's the distance? 0 meters. So did you do any work? No. So you didn't do any work on the car, and that's very deceiving because if you've ever done something like physically like work out at the gym, when you think about it, you pick up your weights, you lift them and put them down, and then you re-rack your weights because you're not animals, right? Rack your weights. But when you do that, the weights are right back to where they started, right? What's the difference in the weights before you were there and after? There is no difference. So there really is no work done on those weights. But here's the thing, do you feel like you did nothing? No, you got some exercise, you burned some calories. So how can we say work is not done? Well, remember, work is the transfer of energy. So in the case of, let's say, pushing the car, if you push the car as hard as you can for 6 hours and it doesn't move, you didn't do any work. You didn't transfer any energy to the car. That doesn't mean you didn't use any energy. Let me ask you a question. If you've ever pushed a car and it didn't move, pushed a car and it didn't move, or you've done exercise, how does that make you feel? Looking for a very specific word. Huh? Exhausted? Okay. That would indicate that you used energy. So where did it go? It's in one of the feelings that you feel after you exercise. Spent? Close? Look for a specific word. Most of y'all have exercised before, right? How do you feel?
Sleepy.
Sleepy? What else? Tired? Keep going. Worn out? Y'all get that? Sore? I'm talking about right after you get done putting those weights down. Sweat? Why are you sweating? But what does sweat do? Why do you need to be cooled down? Because you're hot. Right? turn into heat. Thermal energy. Does that make sense? You get hot, right? So, okay, you didn't do work on the weights, you didn't push the car or whatever, but you still transferred energy. You just didn't transfer energy to that object. Does that make sense? Like if you push the car and it's moving, well now the car has kinetic energy. And you're like, okay, I put energy into that car. But here's the truth. Anytime you transfer energy from one form to another, you always lose some as heat. Okay? So pretty much anytime you do anything, you just feel a little bit warmer, right? Now the second sentence here says, okay, you carry a football 30 meters downfield at a constant rate. How much work did you do? Well, it gives you the answer right there. No work is done. Well, how can that be? Well, this is a little different. Remember, work is force times the distance. So in this case, it's obvious that you're carrying it down the field. It went 30 meters. But the key is right here in the setup. It says you're carrying it at a constant rate. If you're carrying it at a constant rate, remember a rate is something changing over time. If you're just simply walking downfield with a football, are you speeding up? Are you slowing down? No. You're going at a constant speed. So if you're not speeding up or slowing down, are you accelerating? No. So force is mass times acceleration. Well, if there's no acceleration, there is no force. And if there is no force, there is no work. Now, that might seem weird again because you're like, but I'm definitely holding the football up. It's like, yes, you are. But gravity is also pulling it down. And in the end, the ball's not speeding up or slowing down, it's just maintaining its speed. So there's no work being done because the ball hasn't changed its speed. It hasn't sped up or slowed down or exploded or something. So there's no work being done in that situation. Now, if you take the football and throw it, did you do work? Yeah. Because at first the football would be going 0, then you throw it to whatever speed you throw it to. So we got to be a little careful there. I'm not going to try to trick you with these questions, but I want you guys to know that you really got to think about what's going on. Okay, so let's do a little calculation. So it says Jim lifts a 100-Newton barbell over his head. It's a distance of 2 meters, let's say from the floor to over his head. Calculate the work Jim used to lift the barbell. $200 joules. How'd you find that? Yeah, 4 times distance. Was that difficult? No. Like this is a problem I could give you on an audit or quiz. Now because this is so simple, I'm going to give you multi-step problems, but you'll find out that they're all pretty similar to this. So you should also be prepared for problems and be going like, okay, well if you use 200 joules of work, and you lifted 200 meters, or it's like 2 meters, how much does the barbell weigh? So you should be able to go backwards as well. All right, but 200 is the correct answer. So, what about power? So power is another little thing here. So it gives us the formula for power, and it says power is work divided by time. Okay? So work is measured in joules. What's the unit for time? Seconds. And so power is measured in watts. Now that's a unit I know you've heard of. Right? I mean, watts does this light bulb use? Well, typically when you're talking about a light bulb, you're talking about electrical energy in terms of that power, but anything can be measured in watts, right? So watts is a rate at which work is done. That is the definition of power, the rate at which work is done, how quickly you do work. What's really interesting about work and power is that work is simply, moving an object or pushing it faster. Power is how quickly that work is done. So it says right here, if a person carries a Twinkie up a flight of stairs, the amount of work done is the same regardless of how fast you do. Because in the end, the Twinkie started on the bottom floor, now it's on the top floor. It's gained what we call gravitational potential energy. So it'll gain the same amount regardless if you walk up the stairs, run up the stairs, fly up the stairs. It doesn't matter. It will have changed the same amount. But power asks how quickly did you do that work, right? And typically we think of things that display more power as being, stronger, or bigger, which is often the case. So, let's take a look at power. So we have Michael lifts his barbell in 1 second, and Jim lifts his barbell in 10 seconds. Determine the power used by each man during his lift. So we're kind of back to old Jim here. And it says Jim lifted a 100 Newton barbell 2 meters. But Michael also lifts a 100 Newton barbell 2 meters. So before we calculate their power, let's calculate their work. How much work did Jim do? 200 joules. It's the same as the last problem, right? How much work did Michael do? Also 200 joules. It's the same amount of work, right? Now, when it comes to calculating power, well, what's Michael's power? What's 200 divided by 1? 200. So Michael displays a power of 200 watts. Does that make sense? What about Jim's power? 1. You do 200 divided by 10. So, obviously the correct answer here is C. Now, I want you to, physically look at the pictures of Michael and Jim. Do they look the same? Yes, Michael does look big. If you saw these two guys at the gym, which one do you think is stronger? Michael. And that's pretty typical because the whole point of power is it displays how quickly you can do the work. So to emphasize this, Michael basically just grabs the barbell and just lifts it, goes, puts it up 1 second. But if Jim literally took 10 seconds, he's just like, that's like 10 seconds, okay? First of all, 100 newtons is like nothing. So if he's having trouble lifting that, he doesn't have very much muscle. But here's the key. When you're looking at these two guys, obviously Michael has more muscle than Jim. But the key here is that they both did the same amount of work, right? But the difference is Michael's able to do it faster. Now, one of the biggest things that most people don't realize on the surface is that Michael's power comes at a cost. And I don't mean saying as Jim all day. It comes at a cost of energy. Because he did it faster, typically things that do work faster are way less efficient. So it turns out Michael has to eat a lot more food than Jim does. And if you've ever been around athletes, or you are an athlete, or you've seen professional athletes, they eat a lot more food than your average person because they're having to burn more simply to walk around and stuff. And they're going to be a lot less efficient at it. So, it's always a cost. So here, this just gives you what I just said. Since Jim takes 10 times as long, he has 1 minute. All right, so here, there's several slides on horsepower. I'm not going to go through them really, because it's just kind of connecting, what you should know. Most people have heard of horsepower, right? Especially in this country. So it's just another unit of power. It's a unit of power. So we use the watt, but also horsepower is used. And it's defined to be 746 watts. Right? 1 horsepower is equal to 746 watts. So, when we do the lab, I'm going to have you calculate your power in watts, and then I'll have you calculate your horsepower. This is just kind of emphasize this. Here, it gives you a little story about James Watt, who the Watt is named after. And it turns out James Watt was actually an inventor. And he didn't really invent the steam engine, he just simply made a really good version of one. And he sold the steam engine. Which is interesting because you're like, okay, he sold steam engines, and the unit of watts is named after him. So what does this have to do with horsepower? Well, it turns out back in James Watt's day, his main competition wasn't other engine manufacturers, it was horses. Because that's what people had. You had horses to do work. Right? You had horses pull your buggy, you had horses plow your field, stuff like that. So he wanted to compare his engine to a horse. So he went through and he calculated, the next, I think, couple of slides just kind of go through his actual experiment, nobody cares. to figure out how much power a horse produces, okay? And it turns out he came up with this calculation of 746 watts. The important thing to note is most horses do not put out 746 watts of power. At least if they do, they can't do it consistently. If a horse is putting out 746 watts of power, let's say, for an hour, most horses, if you made a horse do that, would be very upset with you. And if you made them do it, say, over the course of a whole day, like an 8-hour shift, the horse would probably die. And so the question has always been, well, okay, why would he claim the horse has more power than it actually does? Because is he a horse salesman? No. He's an engine salesman. And the reason why a lot of people think he did this is either he can't calculate things, or if you say that this engine has, and this is back in the day, I know you buy a truck today that has like 400 horsepower, but I'm talking about this is back in the day when like an engine had like half a horsepower. If the engine has half a horsepower, why would you make it seem worse by saying the horse is stronger? Well, it turns out engines have an advantage horses don't. They can run all day and night. If you have, let's say, a mill and you wish to grind flour, and you say, okay, I'm going to run it all 24 hours a day. You need at least 3 horses to like drag the mill wheel, or at least 3 teams of horses. And it's like, okay, well, you can replace those horses with one engine. Then you start to see the cost effectiveness of the steam engine here. So, what's interesting is that 746 watts is a lot of energy, and a person can put out this much energy. Generally not for any length of time, but, like when we're doing the horsepower lab, some of you might actually come out that you have a horsepower. I've had several students do that. Now granted, they're doing it for like 10 seconds or 3 seconds, but still, you can easily put out more than a horsepower. The key is for how long. So this is all James Watt's experiment. I'm not going. Nobody wants all this. Look, horse, that's how we did it. Okay. Ugh. Like I said, if you're interested in that, it's all there. I'm just not going to go through that sweet history lesson. So if you look at machines, if you buy something, they can have different power ratings, right? Machines with different power ratings do the same work in varying amounts of time. So generally, if a machine has a higher power rating, it will do the same work as another machine, just faster. So a good example of this is actually cars. So I mentioned you could go buy a car that's 400 horsepower. Apparently, nowadays, you can go buy a car that has 2,000 horsepower. Apparently, there's a new McLaren out there that has 500 horsepower per wheel. That's a lot. However, most cars in the parking lot only have 100 or 200 horsepower. So if we take, let's say, a faster car, y'all give me an example of a faster car. Which car do you think is faster? A what? The F1, a race car, right? For those of you who don't know, F1s are like the little Indy style looking cars. I don't know how else to describe it other than, yeah, wings all over. Okay, so an F1 race car. Now give me an example of a slow car. Toyota Prius. Okay. So we're gonna have a drag race between Toyota Prius and an F1 race car. They're just gonna drive down the street, say over a quarter mile. Which one, if I say race it go, which one do you think gets to the end first? The F1, right? But does that mean the Prius doesn't finish the race? No, it totally does. So they can both do the same work. They can both get down the street. However, the F1, with its higher horsepower rating, will do it faster. Does that make sense? Also, it should be noted, which one do you think gets better gas mileage? The Prius. Because again, if you do work faster, you tend to be less efficient. And so here we have different videos of examples of things doing work. And I believe that is the end of the minutes. So I'm going to stop recording. Do y'all have any questions right now?